Okay, hello, good morning, whatever time zone you are in. Welcome to the poster of the study of Beryllium-13. I am Yannick Gueye. I am a freshman at Michigan State University, double majoring in studio art and physics. So the first portion of my PowerPoint is the abstract describing the experiment that ran through September 25th through the 30th. So what happened is they took a beryllium-14 beam, launched it through the telescope, and created beryllium-12. Now, how do we get here, you may ask? Well, we take beryllium-14 and we launch it through the telescope. It hits the target and becomes beryllium-13 and a neutron. Sometimes. I say sometimes because beryllium-13 happens once in 1,000. So it happens, but not so often. And then beryllium-13 is also an unbound isotope. This means that it does not last very long and it wants to remove itself from the equation. And it does this by removing a neutron and becoming beryllium-12 and a neutron. So beryllium-12 lasts longer than beryllium-13. So it'll actually go through all the way through the telescope and stop somewhere in the cesium iodide, shown right here, giving us the particle range, which we'll return to later. But so the neutron will actually go through all the way and go into the Mona Lisa telescope right here. Now, beryllium-12 is also created in an excited state. This means it cannot stay excited forever. It's like when you get a puppy. You're excited, I got a puppy, but during the next week, you're like, that's just my dog. It's the same thing from beryllium-12. It has to calm down, and the energy that it gives off are called gamma rays, which we are also detecting. This is what we actually look at. The methods I use is the G4 beamline. It is a simulation of Giant 4 Monte Carlo, and it allowed me to run the simulation with different energies and physics and discover what happens. I also use Root to generate histogram plots as shown here, which is this is proton versus neutron, and I'll return to these results later. And I also use Least plus Fuss for calculations and MATLAB for some graphs like here. So the results, we identified 7 isotopes using 76 MeV per nucleon and also 100. Some physics that I used actually didn't work. That just meant that it was wrong for our work, but some physics actually did work. Now, the results shown here are the proton versus neutron, and you can see the different graphs and how they correlate. My next step in future is to see what happens and compares between G4 beamline and Least plus plus. I say the comparison because G4 beamline will actually give you the distributions of the particle ranges inside cesium iodide and will show you the different beams and where they stop inside. Whereas Least plus plus, if you put in beryllium-12 or 13 or whatever you want to calculate, it will only give you the average. It'll say it should stop around here somewhere. But G4 beamline will give you the actual distribution. But sometimes it's not always right. Whereas beryllium-12 only happens once in a blue moon because of beryllium-13. You're not going to get that many results. You might get 1 in 1,000, like I said. So the average wouldn't have that much to go off of if you don't have a lot of results. Whereas G4 beamline would give you those actual results. So I want to see how they compare and also to calculate it. So that's it. So thank you for your time.